Hi everyone, in this video I'm going to be talking about molarity. Molarity is a way we measure concentrations of solutions. Remember, the solution is something dissolved in something else. The vocab terms we use are a solute dissolved in a solvent. Remember, water is a universal solvent, so water is usually going to be the solvent in our solutions. In fact, anytime you see aqueous, aqueous, aqua, that's water. So in this video, we're going to go over defining and understanding molarity, solving simple molarity problems using M equals moles over liters, calculating how to make solutions, meaning like in a lab setting, and we're going to finally end with some molarity stoichiometry problems. So starting off with molarity, again, what is molarity? Well, molarity is a measure of concentration. Molarity. It's a measure of concentration of solutions. Concentration of solutions. By definition, molarity, which has a capital letter M, is moles of solute divided by liters of solution. Moles of solute divided by liters of solution. Now, in Chem 1-2, we're just going to simplify this down to molarity equals moles over liters, or sometimes you'll see it written as M equals N over L, where N is number of moles. I usually say number of particles for N, but M equals N over L as long as N equals moles. So I tend to go with this formula here, molarity equals moles over liters. Now, if you go into higher levels of chemistry, you'll learn that this isn't the only measure of concentration. There's several others. There's percent by mass, there's molality, there's molar, I'm blanking here, but there's several other methods. So you might have to dive a little deeper than just saying molarity equals moles per liter. But for us, we're only going to be using molarity as our measure of concentrations. It is the most common one. So we can just simplify it to moles per liter. You don't need to say moles of solute per liter of solution. Okay, so molarity equals moles per liter. Now, you might think back to when we did the density formula at the start of the year, where D equals M over V, we formed this pyramid. You remember the DMV pyramid? That mountain of paperwork that you needed to go over, DMV? This was useful because you could cover up any of these three letters and you'd get your formula. Well, the same formula can get us the molarity formula can get us a pretty similar triangle here. So molarity, which is capital M, equals moles over liters. So we can write it like this. Molarity, moles, liters. And as long as you memorize that order, this can be a helpful tool because molarity, cover that up, is moles per liter. Liters, cover that up, is moles over molarity. And if you cover moles up, moles equals molarity times liters. Okay, so this is a tool you can use if you want, or you could always just have the formula memorized and algebraically rearrange it to solve for what you're looking for. Now keep in mind, the volume has to be in liters to use a molarity formula. You cannot use milliliters for this. It has to be in liters. So just understanding molarity kind of as a concept, let's kind of visualize what a concentration would really look like. So imagine you have a beaker of water here, and you have some kind of compound that you want to dissolve in it. Now, most compounds, we tend to talk about ionic compounds in this case. You could have some covalent compounds, but it's a lot more rare. Usually we have an ionic compound and they are almost always solid and they're almost always crystally white solids. Like picture salt, table salt, NaCl, that's one example. So let's say you have like a little pile of white crystally solid down here. And if you were to really look at that, it would look something like, and not literally like this, but it would be something like, if we're doing NaCl, it would be like Na bonded to Cl, bonded to Na, bonded to Cl. And this will repeat in all three dimensions over and over again, just to visually see this. Three-dimensional image here. And if that were to go in the water, it would split into ions. The water would essentially pull it apart like piranhas attacking a piece of meat. It's going to pick it apart. And you're going to end up with these ions floating around in water. And depending on their charges, the waters are going to orient themselves in a certain direction around that. So molarity is a measure of the moles of solute divided by the volume of solution, or not really volume, it's liters of solution. So if you took exactly 1 mole of NaCl and dissolved it in exactly 1 liter of water, well, enough water to form exactly 1 liter of solution, then your calculation for molarity would be 1.00, I'm just making up 3 sig figs here. Imagine you have 1.00 moles divided by 1.00 liters, your molarity is obviously going to be 1. Well, technically with 3 sig figs, 1.00. And the way we're going to write that, like the unit essentially, is just a capital M for molar. So that's going to give us a molarity of 1.00 M. That's how you would write it. And the way we say that is 1.00 molar, like M-O-L-A-R is how we phrase it. Or you could say the molarity is 1.00. Although it's more common to say this is a 1.00 molar solution. If you add 0.50 moles in that 1 liter, then it would be 0.50 molar solution. So it's very simple. The formula is for molarity is moles divided by liters. So let's go through some examples. So using the molarity triangle, or the formula molarity equals moles over liters, we can work out some simple types of problems. Let me just move this real quick. Oops. All right, so what is the molarity of an 80.2 milliliter solution containing 0.328 moles of dissolved sodium sulfate? So we're looking for molarity. Keep in mind that molarity equals moles over liters. Or if you use a triangle, you get the same thing. All right, let's see what we're given. Well, we're given this volume of solution, but we're not given it in liters. So that you're going to be doing this quite a lot, converting milliliters into liters. To do this, you can either divide it by 1,000, because essentially it's 1 liter per 1,000 milliliters, or grab the decimal, sweep it 3 times. So this would give us 0.0802 liters. So that's my volume. And 0.328 moles, it already gives us moles. So it's very simple. Molarity equals moles per liters, which in this case is 0.328 moles divided by 0.0802 liters. This is going to be a really concentrated solution. 0.328 divided by 0.0802 gives us, that's not too bad, 4.089, we'll call it 4.09 molar. I guess technically another way you could write this, it's less common, but it is correct, would be moles per liter. So either of those would be acceptable answers. And again, the way you would phrase this, 4.09 molar. Now, in this case, it gave you moles, but in most cases, you're not going to be given moles. You're going to be given grams. And you've probably figured it out by now. When you're given grams, you're probably going to end up converting them into moles, and you're doing the same thing for these types of problems. A student dissolves 16.2 grams of aluminum chloride in enough water to make 125 milliliters of solution. What's the molarity? All right, so again, molarity, capital M, equals moles per liter. So I'm given grams, I'm not given moles, but we know how to convert that. So we're going to need to take 16.2 grams of aluminum chloride. This is Al3+, this is Cl-, AlCl3. All right, so to convert this from grams to moles, it's going to be times 1 mole over, let's see, aluminum is 26.98 plus 3 chlorines. So I got about 133.33 grams per mole. Gram cancels gram. and I end up getting 0.122 moles of AlCl3. All right, so we worked out the moles. I'll plug that right in. We are given milliliters, 125. So we're going to grab that decimal point, which is right here, sweep it 3 times to give us 0.125 liters, and that's going to plug right in there, 0.125 liters. So it actually looks like it's going to be almost exactly 1 molar, will be a little bit less. So 0.122 divided by 0.125 with 3 sig figs, 0.976 molar. 0.976 molar. Or you could write that as 0.976 moles per liter. All right, in this problem, it says what mass of silver nitrate are dissolved, should say is. I think I originally wrote how many grams of. So what mass of silver nitrate is dissolved in 47.2 milliliters of 0.850 molar solution? So notice I'm not asking for molarity anymore. Remember, the molarity triangle goes like this. Molarity, moles, liters. So what are we looking for here? Well, we're looking for mass, but notice how mass isn't in the triangle. Well, mass and moles can always be interchanged using molar mass conversions. So in this case, we're going to use the molarity triangle to solve for moles and then just turn it into grams. Now, in order to do that, we need to be given molarity and volume. Are we given those? We're given volume. We're given molarity. Yes. All right, so we're going to be solving for moles. So moles equals, according to the triangle, we cover moles up with our hand, molarity times liters. All right, so molarity is 0.850 molar. Now, this is when I actually prefer to write it instead of just M. I prefer to write it as moles per liter because now we're going to see the units cancel out. So my 0.850, 0.850 moles per liter, okay, that's my molarity. And I just need to multiply this by my liters. All right, 47.2 milliliters, sweep that 3 times. That's going to give us 0.0472 liters. And notice by writing molarity as moles per liter, see how the unit cancels? Liter cancels liter, and we're left with moles, which makes sense. 0.850 times 0.0472 gives me 0.0401 moles of silver nitrate, AgNO3. Okay, so we found moles, now we just need to find grams. So we go from moles to grams using molar mass. All right, I'm looking at the periodic table. So Ag is 107.87. N, one of those, 14.01, plus 3 O's, 16 times 3 is 48. 169.88 grams per mole. So that goes on top. 169.88 grams over 1 mole. Multiply these together. And with 3 sig figs, I get 6.81 grams. 6.81 grams. Okay, so what mass of silver nitrate is dissolved? Right there. So if you want to picture actually working with this in the lab, you would open up your container of silver nitrate. You would scoop out 8.61 grams. You would add enough water to make 47.2 milliliters. And then there's your 0.850 molar solution. What volume of solution is needed? So notice we're solving for the last of them, volume. Let's work out our equation before we even do anything else. So molarity equals moles over liter. So we can say molarity, moles, liters. That's my triangle. We're solving for volume. Now it doesn't clarify what unit, so we can leave it as liters. So liters are going to be equal to moles over molarity. Now let's say you forgot how to do the triangle thing, okay? Just ignoring that. How would we solve for liters? Well, excuse me, as long as you know the formula for molarity is molarity equals moles over liters, you can work this out. Now, how do we isolate a denominator? It's a little tricky. I advise you do it in 2 steps. First, get rid of denominators. I hate denominators. I want them to go away. How can I get rid of this denominator? Well, I can multiply both sides by liters. So by multiplying both sides by liters, my liters go away over here, and they end up over here. So liters times molarity equals moles. And now if I ask you to solve for liters, it's very simple. We divide by molarity. So liters equals moles divided by molarity. All right, which is the same thing we had before. Okay. So my molarity is given 1.50 molar. Let's just plug that right in. And for this, I'm going to put it as moles per liter so we see the units cancel. You can leave it as molar though. If we have 5.82 grams of the solid compound of lithium bromide, so turn that into moles. 5.82 grams of LiBr. So lithium bromide is going to be 6.941. That's lithium. Bromide is 79.90. Add those together, I get 86.84. 86.84 grams. 5.82 divided by this gives me 0.0670 moles. So that's my moles, 0.0670 moles. All right, in terms of units, mole cancels mole. I'm left with liters as my double denominator, I call it. It's like the denominator of the denominator. That ends up being our unit at the top. So 0.0670 divided by 1.50 with 3 sig figs. My answer is 0.0447. Now, in terms of unit, what's left? Liters. And since the problem didn't ask for milliliters, we can leave it like that. Or if it asks for milliliters, or even if it doesn't, it's much more convenient to put this in milliliters. We sweep that decimal point 3 times to the right now, multiplying it by 1,000 milliliters per liter. And that's going to give us 44.7 milliliters. All right, so either of those would be acceptable answers here. Okay, so you should be able to manipulate the molarity formula to work out simple questions like this. Kind of like how when we did density problems, be able to solve for D, be able to solve for M, be able to solve for V. The next thing we can do with molarity is calculate how to make solutions, or sometimes we even call them stock solutions. A stock solution is like when you make one master set of solution, in a big jug, and then from that you kind of take small samples out of it. That would be like a stock solution. So here's an example. Determine how to make a 125 milliliter sample of 0.750 molar calcium iodide solution. It's very simple. When you're asked to calculate how to make solutions, you'll usually be given the molarity and the volume you're looking for. So all we need to do is solve for moles. And then once you solve for moles, you solve for grams. So essentially, calculating this is just find grams. And then what it would end up being is like the instructions would be, let's say the answer ends up being 38.5 grams. Well, you would add 38.5 grams into enough solution to make 125 milliliters. And then you have your solution. All right, so let's work through this one. We're looking for moles, which we can then solve for grams. So molarity equals moles over liters. So that's our triangle. To solve for moles, it's going to be molarity times liters. So moles equals molarity times liters, which is 0.750 moles per liter times liters. 125 milliliters is 0.125 liters. All All right, 0.750 times 0.125 gives me 0.09375 or 0.0938 moles. 0.0938 moles. All right, so that's how many moles of calcium iodide we would actually need. We now need to turn this into grams to finish out the problem. So 0.0938 moles. Now calcium iodide, now is when we got to know the formula. It's going to be CaI2. So 40.08, that's my calcium, plus 2 iodides, 126.90. 4 plus 2, okay, so 293.88 is a molar mass. So times 293.88 grams per 1 mole equals 27.6 grams of CaI2. Okay. Now, just putting this as like the answer, it's not really answering the question. It says determine how to make a 125 milliliter sample. So your answer would be like putting this in a sentence form. It would be dissolve 27.6 grams of CaI2 in enough water to make 125 milliliters of solution. And you might say, can't you just say dissolve that in 125 milliliters of water? It'll end up being very close to that. But since technically molarity is moles of solute divided by liters of solution, we want to make sure we're clear that it's that many milliliters of solution. It's just the proper way to phrase this. So essentially, you're solving for how many grams you would use. And then like if this were a real lab scenario, you would actually take your bottle of calcium iodide, you would sit it next to your balance, you would scoop out 27.6 grams very carefully, and then you would add that to water. And what we generally do, just so you can kind of look ahead at where we're going, because we will be making some of these in lab, you generally take a round bottom flask, and this has like a line on it that says whatever, might be like 100.00 milliliters. So what you would do is you would add your 27.6 grams of solid, and clump at the bottom like that. And then you add a bunch of water to it, so it fills up about this much. Now, why wouldn't you fill all the way to the 100 line? Because you're going to need to dissolve that. And if you only leave yourself this little bit of air, it's tough to dissolve it. So what you do is you fill it up to about here, and then you cover the end with your thumb, with a glove, and you shake, and you just shake it until it all dissolves. And then you have to top it off with water to get exactly to that 100 line. So now you have all of that dissolved solid up to a perfect 100 milliliters or however much you need. And then that's your solution. Now in this case, I didn't say 100, I said 125. So you would just maybe make this and then add it to 25 more milliliters. But that's the process that we'll eventually be going through. All right, here's one more sample problem of how to calculate, or how to make a solution here. So calculate how to make a 20.0 milliliter sample of 0.400 molar zinc chloride. All right, so remember what we're looking to do is find how many grams of zinc chloride are we going to need to add to make this solution. Now there are no grams in the formula, so we find moles. So molarity equals moles over liter. So moles are going to equal molarity times liters, which in this case equals 0.400 moles per liter. That's my molarity. Times liters. 20.0 milliliters, sweep that 3 times. That's going to be 0.0200 liters. And yes, I have to keep those 2 zeros because they are sig figs. All right, calculator. 0.400 times 0.0200 gives me 0.008. But we're going to add those 2 extra zeros at the end for sig figs. 0.00800. and my unit, liter cancels liter, is moles. So that's how many moles of zinc chloride we need. I could even write ZnCl2. And now we just need to convert that to grams. So 0.00800 moles of ZnCl2. Zinc chloride, 65.39 is zinc, 38, according to that, plus 2 times 35.45 gives me 136.28 grams per mole. And with 3 sig figs, I get 1.09 grams of ZnCl2. Okay. So to answer the question, it would be something like dissolve 1.09 grams of ZnCl2 in enough water to make 20.0 milliliters of solution. And again, what that would look like in a real lab scenario, you would take one of those circular vessels, one of those round flasks, you would add your 1.09 grams of solid. And remember, as I said before, most ionic compounds tend to be white solids. But if you were to open a new tab right now and Google zinc chloride, and go to images, you'd probably see like a white crystalline solid. Yeah, you'd add your 1.09 grams of that, and then you would add most of the water you need, not all of it. Then you shake, 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 shake to get it to dissolve. And then once it's dissolved, you top it off very carefully with water to get it exactly to your 20 milliliters. Okay. So the last concept we'll cover here is molarity stoichiometry. And you might be saying, stoichiometry, it just took us 2 weeks to cover stoich. We're now going to do a whole nother segment of stoich. Well, it's very easy. In fact, it's easier. You're going to grow to love molarity stoichiometry problems because you actually don't have to do molar mass calculations, at least for your reactants. So remember, up until now, anytime you've had a stoichiometry problem, you've been given the grams of this reactant, possibly the grams of another reactant, and you're asked to find like the grams of a product. Or maybe you're given the grams of a product and asked to find how many grams of the reactant reacted. Well, now we don't have to tell you grams because we have another way of finding moles. Moles can now be found using molarity times volume times milliliter times liters. So for molarity stoichiometry problems, they're just regular stoichiometry problems, but instead of being given the grams of one of the reactants, you can now be given the molarity and the volume. And it's just, you just solve for moles, and then you're back in familiar territory. All right, so if 6.08 milliliters of 3.11 molar rubidium sulfate solution react with excess sodium hydroxide, how many grams of rubidium hydroxide will form? All right, so just like every other problem we've done, start with a balanced equation. Rubidium sulfate, rubidium is Rb plus, sulfate is SO42 minus. So we crisscross it, it's going to be Rb2 SO4, and it's a solution, so I know it's aqueous. React with excess sodium hydroxide. So sodium hydroxide, that's going to be Na plus, OH minus, so it's simply NaOH. Now I didn't indicate the state here, so we're just going to leave it like that. Okay, type of reaction. Well, I have AB, CD, so it's going to be a double replacement. Rubidium is going to bond with hydroxide. Hydroxide is OH minus, so it's going to be RbOH. Sodium is going to bond with sulfate, which Na is plus, so we're going to get Na2SO4. Now, in terms of states, we generally would want to predict the states here, but I believe the pink sheet we use doesn't have rubidium on it. But in this case, I'm just asking for grams of rubidium hydroxide, so I know that's what we're solving for. Okay, the equation's done. Now we balance it. Notice nothing different. 2 rubidiums, 1 rubidium, so let me put a 2 here. That's 2 hydroxides and 1 hydroxide. Let me put a 2 here. two sodiums, and we're good, giving us a 1, 2, 2, 1 mole ratio. All right, so now's the only time it's different. And up until now, I would have told you how many grams of rubidium sulfate you have. But now I told you volume and molarity. But you can just solve for moles using that simple formula. So moles equals molarity times liters. Might not be a bad variation to just memorize that. You know, I told you molarity equals moles per liter, so you should be able to work out that moles equals molarity times liter. You're going to be doing this variation quite a lot. All right, so in this case, my molarity is 3.11 moles per liter, and my volume is 6.08. Now with volumes less than 10, you got to be a little careful here for milliliters. So we have 3 times and have 2 zeros after the decimal. So 1, 2, 3, it's going to be 0.00608. So just be careful with that. 0.00608 liters. Liter cancels liter. 3.11 times 0.00608 gives us 0.0189 moles of rubidium sulfate. Okay. And now we're back in familiar territory. You just take this number, you plug it in under the rubidium sulfate, 0.0189. It tells you we have excess sodium hydroxide, which means we don't have to worry about limiting reactants. We know that this is going to be my LR, so we're basing it off this. You can even write in excess if you want, but it's not necessary. We're looking to solve for rubidium hydroxide, so we'll put my X right here. We're going to apply a 1 to 2 mole ratio. So we're going to double this. 0.0189 times 2 gives me 0.0378. And that's moles. And the problem asks you for grams of rubidium hydroxide. So we just got to do a moles to gram conversion. So 0.0378 moles of rubidium hydroxide times molar mass. So rubidium is 85.47 plus 1 oxygen plus 1 hydrogen, 102.48 grams over 1 mole times 0.0378. And with 3 sig figs, my final answer, 3.87 grams of RBOH. So let's just take a sec, decompress, and just realize like what's different about this. It's only one thing. Instead of being given grams, which you turn into moles using molar mass, you're given volume and molarity, which you can turn into moles using the molarity formula. And you see how I said you'll probably like this better? Notice we didn't need to find the molar mass of rubidium sulfate. It's actually kind of nice. Now we did need to find the molar mass of the product we're looking for, but for the reactant or reactants, if there were another, we wouldn't actually need to do that. All right, so we have just one last problem in this video. I made it quite comprehensive to kind of sum up everything we've done so far. 16.0 milliliters of 0.850 molar calcium chloride are mixed with 75.0 milliliters of 0.110 molar ammonium phosphate. What mass of precipitation should form? If this many grams are collected, what's the percent yield? And sketch the reaction. Okay. So I kind of started it out over on this slide. First thing, balanced equation. So calcium chloride is CaCl2. Now, I didn't say solution, but I don't have to anymore. If I tell you molarity of it, it has to be a solution. So that means aqueous. 75.0 milliliters of ammonium phosphate is going to be NH4, parentheses 3, PO4. And again, because I told you the molarity of it, it means it has to be a solution, which means it has to be aqueous. All right, double replacement. So calcium bonds with phosphate, giving us Ca3 parentheses PO4 close parentheses 2. Ammonium bonds with chloride, giving us NH4Cl. All right, now we need to know the mass of precipitate that should form, so we need to know which of these is the precipitate. And you use your solubility table, and you'll see that ammonium chloride is aqueous, and you'll see that calcium phosphate is solid. And now we have to balance this out. 3 calciums, 1 calcium, so let's put a 3 there. 6 chlorides there, 6 ammoniums here, 6, 2 phosphates, 2 phosphates. So we have a 3, 2, 1, 6 ratio. Now this would normally be the point where you need to take both starting masses, turn them both into moles, and plug both numbers in. Well, now we don't have masses, but we have volumes and molarities for each of them. All right, so 16.0 milliliters and 0.850 molar. So remember, moles equals molarity times liters. So for this first one, my molarity is 0.850 moles per liter. Just making sure. Okay, and I have 16.0 milliliters. That's going to be 0.0160 liters. 0.850 times 0.016 gives me 0.136. Oh, I forgot a 0. 0.0136 moles of calcium chloride. All right, so that fills right in, 0.0136. Now, I also told you how much ammonium phosphate. It's 75.0 milliliters of 0.110 molar. So we're going to do the same thing. So the molarity is 0.110 moles per liter. And the liters is 75 milliliters, 75.0. We sweep it 3 times, which gives us 0.0750 liters. 0.00825 moles of NH4,3PO4, ammonium phosphate. 0.00825. Okay. And now we're back in familiar territory. You're going to solve this one out just like you would have before this video. All right, we're given both reactants, so we need to identify the LR. So the way I like doing this, grab my smaller coefficient first and say to myself, it's a 2 to 3 ratio, meaning I need 1.5 times more of this one to react all of this one. Let's see if we have 1.5 times more. 0.00825 times 1.5 is 0.0124. Do I have 0.0124? Yes, I do. I have more than enough excess reactant, limiting reactant. If you use a different process for finding limiting, that's fine, as long as you identify the right one. All right, now we're looking for the precipitate, the mass of the precipitate, which is my solid product. So here's my X. So I'm going to go from my limiting to my X, apply a 2 to 1 ratio. 0.00825 divided by 2 is 0.00413 moles of calcium phosphate. All right, so we got to now do a mole to gram conversion, 0.00413 moles. So molar mass, so 3 calciums plus 2 phosphoruses plus 8 oxygens gives me a molar mass of 230.02. Mole cancels mole. And I got 0.9499, which is 0.950. grams of Ca3PO4 2. So the answer for part A is right here. That's how much you should get, 0.950. Let's go all the way back here, 0.950. All right, part B, if 0.601 grams are collected, what's the percent yield? So it's how much you got in your experiment divided by how much you should have gotten times 100%, 0.601 over 0.950, 63.3%. That's part B. And finally, part C, sketch. So nothing different than what we did before with limiting reactants. All right, so calcium chloride, ammonium phosphate. Beaker number 1 plus beaker number 2 yields beaker number 3. All right, so in the first beaker, I have my calcium ion and my chloride ion. In my second beaker, I have my ammonium ion and my phosphate ion. Final beaker, I have calcium phosphate as my solid precipitate at the bottom. I have my aqueous product, which is the ammonium chloride. So I have ammonium and I have chloride. And now before I add the waters, I need to add my third ion, which is the excess reactant. Looking back here, my excess reactant was calcium chloride, meaning I have extra aqueous calcium chloride floating around in that final beaker. Now, one of those is already going to be there, chloride. So I need to add calcium. And now we just add a few waters and we're good. Make sure the waters face the appropriate direction like this. And that's it. So molarity stoichiometry probably saves you a little time because notice in terms of molar masses, I lost where I was working here. We didn't need molar mass to get moles of either. We just used the molarity formula. Now we did end up needing molar mass to find the mass of precipitate, but only once is better than 3 times. Okay, thanks for paying attention and good luck working on molarity problems.